Okay, here's the central limit theorem problem, and before you do this you might make sure that you can find areas under the normal curve. You'll have to be able to do this pretty readily for this problem. And here it is: an officer in the Army needs 35 men for a mission. He wants these soldiers to be smart enough to understand the details of the mission, so the average IQ of the 35 men must be greater than 98 points. It is known that the average IQ of soldiers is 96 points with a standard deviation of 16 points. If the officer is given a simple random sample of 35 soldiers for the mission, what is the probability he will get what he wants? In other words, with this simple random sample of 35 men, will the average IQ be greater than 98? That's the question. Okay? Well, let's take a look at the sample that we've given, or the population in the sample. Here I've got them both here. Here's the population parameters. They're called parameters if they refer to the population. The average IQ of a soldier is 96 points in the population. The standard deviation of the soldier is 16 points, and of course the number in the Army is very large. We have a lot of people in the Army. Our sample statistics go like this. The particular sample we get, and I put an asterisk next to this x bar because this is the one we're going to get. We're talking about a specific sample that we're going to get, but we don't know the mean of that sample. We don't know the standard deviation, but we know the size is 35. So our number in our sample is greater than or equal to 30 for sure, and the size of the sample is small when compared to everyone in the Army. In other words, the total of the people in the Army, right? Thus, the central limit theorem applies. All right, so we've got it made. The central limit theorem applies, and here's what that means for us. That first of all, if we took billions of samples of size 35, simple random samples of size 35, and we took the means of each one of those samples, then they'd form a nice normal distribution. The mean of all the x bars would equal mean of the population. We know that, 96, right? And the standard deviation of this normal distribution would be equal to the standard deviation of the population divided by the square root of the number of people in the sample. In this case, that's 16 divided by the square root of 35, which gives us about 2.704 IQ points. All right, so that's our situation. Remember, we want we want the average of our particular sample to be greater than 98. We want to know what the probability that it will be. The average of our sample, the one he gets, will be greater than 98. Well, that's not too hard to find. It's just the area in this tail, okay? And if you know how to find, so the probability that our x bar, the little asterisk, see there, is greater than 98 is equal to 0.5 minus this area here. Why? Because we can find the area from here to here. We know the total area in this side of the normal curve is 0.5, so we subtract that area. And we do that in the usual way. We take the distance from here to here, which is 2 points, 98 minus 96, divide it by the size of the standard deviation, sigma of x bar, and we get about 0.74 standard deviations from here to here. And then we look it up on the chart and we find that area is about 0.2704. Okay. Now, so the probability that the average IQ of our sample, the probability that it's greater than 98 equals 0.5 minus 0.2704, which is 0.2296, or about 23%. So let's see what the conclusion of this is. About 23% of the time, the officer will get a group of men that have an average IQ above 98. I would think this is very good information for him.